Okay, so recording is started. So what I wanted to do today, pick up right where we left off last class, but just a few quick announcements. If you look back in the classroom, um, under course content, I opened up next week's folder. So next Thursday, 2/18, we have our first exam. So that exam is going to be taken during class. We'll hop on Zoom for it, and mostly what that'll be is the I'll be on Zoom in case anybody has any questions, but there won't be a lecture for it. But everyone should log on to Zoom just to start the exam, so I can walk you through the requirements for that. There is an old exam I have here, so if you want to download this exam, I don't have the solution set for you. But if you wanted to try this exam and then ask me any questions about it, I'd be more than happy to answer any questions over during class next Tuesday for you.
Excuse me, where was the exam again?
I'm sorry, Bob.
Where was the exam again?
I'll show you. If you go back into course content under the week 4, of course content, I opened up a week 4 folder there.
Got it, sample exam.
The only thing about the sample exam I just want to say is question number 4, it doesn't relate to the remote course anymore. So when you go look through the sample exam, just don't bother with question number 4. But the rest of the questions kind of mirror, what I would ask on an exam. Also, your homework number 2 is due. That's posted. That's due next Thursday. After class today, you should be able to solve all of it. I'm going to try to get to most of how you would handle question 6 today. So hopefully we can get to that. So I'll also take questions for that on Tuesday. Then next Tuesday, the 16th, how will these apply for extensions? Do you mean like extra time, Marissa, things like that? Yeah, I'll just give extra time in class. You'll just have an extra, you can email me and you can start the exam out, however long early or stay after. Either one works fine for me. But if anybody does have extra time, just email me as we get closer next week of how you'd like to handle it, and we'll go from there. Is that okay, Marissa? Or anyone else? Okay, great. Anything else? What else am I forgetting? So Tuesday we'll finish up regression, and we'll do a little bit of a review during the second hour of class. Okay. Does anybody have any other questions for me before we get started?
Oh, I have a question about the homework.
Yeah. Did I not post Tuesday's lecture? Oh, I did not. Oh,
no.
Thank you. I'll do that. Let me just see. Sorry, it's just been a weird week for me. Where? I'll have to look for it. Shoot. I'm so stupid. Why didn't I do that? Yeah, I'll post Tuesday's lecture after class. Let me just put it on my to-do list here. I'll try to put it up during our break so that I can get it. Sorry about that. And I'm sorry to cut off whoever asked a question about the homework.
Oh, I did.
Yeah, sure. Go ahead.
For number 3, I know we went over everything in the word problem, like standard deviation, but do we learn how to, I don't know if it's like me not understanding the question or if it's.
Question number 3 is a hard problem. Question number 3 isn't like I've covered a problem like it in class. It involves a little bit of like problem solving on it. So like you don't need to calculate the mean or standard deviation. So like a manufacturer of bolts has a quality control policy that requires to destroy any bolts that are more than 2 standard deviations from the mean, right? So what this is saying is, look, if you make a bolt that's too big or too small, we've got to get rid of it, okay? So quality control engineer knows that bolts coming off the assembly line have lengths that follow a normal distribution. and a mean. So I give you the mean and standard deviation. So if the mean is 8 centimeters and the standard deviation is 0.5 centimeters, any bolt that's more than 2 centimeters above the mean, or 2 standard deviations above the mean, or 2 standard deviations below the mean, would be destroyed. So you have to figure out what those values are.
Okay.
It's actually like it seems like a weird problem, but the calculations, it's actually the easiest calculation on the homework. It's just like figuring out exactly what I'm asking.
Yeah.
Is the hard part. Yep. But I promise you, it's just like both these questions are just a simple addition subtraction problem.
All right. Thank you.
But give it a shot over the weekend, and then I'll answer questions on Tuesday. All right. Any other questions? Yes, Melissa. Yeah. It's more than, because it says more than, not more than equal to, more than. Okay. All right, let's get started. Take out your either your TI-84 or your TI-83. I'm going to focus on using the TI-84 in class today. The options and everything, all the calculations will come out the same if you have a TI-83, and the inputs are exactly the same. So let's see where we were.
Professor, really quickly, what are the buttons to refresh it really quickly?
What do you mean by refresh it? Reset it? Like,
yeah.
So, but remember we changed the default setting. Do you remember how to go back? Like but if you want to reset it, you would go second function memory and then 712.
Thank you.
Okay. All right. So I think at the end of class last time, we were working on this, value of R, the linear correlation coefficient. And we did this one problem in our calculator. Let me go back. About hours of study and exam score. Does that ring a bell to us?
Yes, Professor.
Okay. All right. And we said, look, this linear correlation coefficient, it's a value that's always between -1 and 1. Closer to 1, you mean you have evidence of strong positive linear relationship. Closer to -1, you have evidence of a strong negative linear relationship. And what we saw when we did this is this is what we did last class. This is what we did last class. We had we saw that R was equal to 0.9943. So it was like really, really close to 1. And we said, look, there's evidence of a strong positive linear relationship. Okay, so what I want to do today is I want to do another example of this. Okay. So here's this problem. And I'm not going to tell you what the variables are just yet. Okay, but suppose we have these two variables here. Okay, variable 1 and variable 2. We'll assume that variable 1 is our X variable, and we'll assume variable 2 is our Y variable. Okay. What this means is that X variable here is what we call the explanatory variable. And the Y variable is what we call the response variable. Okay. And here's what I want to do. I want to look at the scatter plot, describe the relationship, and then calculate R. All right. So it's a little bit of a arduous process to do that. So everybody grab your calculator, and hopefully you haven't changed any of the settings from last class. Okay. So if I want to input data, does anybody remember what button I have to start pressing with?
Stat.
I'm going to press the stat button, and under number 1 here, I'm just going to hit enter. And what you should have here, okay, is you should have the data from the previous class. So just scroll to the top of each list. And once you have the black highlighter on it, just hit clear, enter.
I have-
Scroll.
Again.
I'm sorry, did I cut you off?
Yeah, I have to input it again. I think I cleared my calc.
That's okay if you cleared it, that's fine.
Can you put those numbers up again?
No. We want those numbers gone. What we're gonna do is Bob, you see the numbers on the screen here now?
Yes, sir.
We're gonna put these in now. And listen to me, you have to be very meticulous when you put these in. So for now, we're just gonna assume variable one is the X variable. So under L1, we're gonna start inputting all these numbers. Okay, so 29.8, 30.1, 30.5, 30.6, 31.3, 31.7, 32.6, 33.1, 32.7, and then 32.8, just like that. Now we're going to scroll over to L2. All right, and you have to put in these variables. 327, 456, 509, 497, 596, 573, 661, 741, 809, and then 717. Okay. So it's a little bit of a pain to put them in, but you just have to, the more practice you get with this, it'll become like second nature to you, and it won't be too bad.
Can you slow down just a little bit, please?
Yep. Yeah, I'll slow down for you. So the hope is that everybody still has the same settings that we did on Tuesday. Okay. So I'm just gonna make sure that we have those settings as I start this example.
Okay, thank you.
Yep, no problem. So everybody just go to second function and then your stat plot. And just make sure it says plot one ... on, and you see the scatter plot selected, this right here. Okay. And if it's not, just turn your plot on and go from there. Okay.
How do you turn the plot on?
Does yours say off, Bob?
Yes.
Okay, hit under number one, just hit enter. And then you should have this light flashing on, just hit enter again.
Wait, so we're gonna basically be switching between that and the box plot, right? When we need it, the scatter plot and the box plot.
Yeah, yes. Yep. Those are really the only graphs we're going to do in this class on the calculator. Yes.
Okay, it's my calculator matches yours.
Okay, good. All right, let's now go to everybody hit zoom on your calculator. And then it's option number 9. We want zoom stat, so you can just hit 9. And you should see something like this. Okay, how many people see this on their screen with me?
What do you hit enter? After you
Yeah.
hit the zoom button?
Yep, zoom. You hit zoom, Bob, and then number 9. Yeah, Jamie, you raised your hand.
Sorry, I meant to thumbs it up.
Oh, okay, no problem. All right.
All I got is a square graph.
All right, Bob. We'll when we go to break, just follow along on my screen for now.
Very good. Thank you.
Yep. Okay, so when you look at this graph, at least on my screen, okay. So the first thing we did was we wanted to look at the scatter plot. Great, we got it. So now the next thing we want to do is describe the relationship. Okay. Does this look, while it's not perfect, does it look like it's a positive linear relationship here?
Yes.
Yeah, absolutely. It's not perfect, but sure does. Looks like as variable 1 increases, so does variable 2. So it looks like we have a positive linear relationship. Okay. And so the next thing it says is calculate the value of R. Okay, so everybody, the next button you're gonna press, we're gonna go back and we're gonna hit our stat. We're gonna scroll over to calc. And does anybody remember the option we used for this?
4.
Yep, LinReg, number 4. So you can just press number 4 on your calculator. If you have a TI-83, it just says LinReg AX plus B, just hit enter. If you have a TI-84, you scroll down to calculate and hit enter. How many people see this? Got it, yep.
Two.
You don't have R, Kayla, so you got to turn on your diagnostic, which we did last class. So I'm just gonna, does anybody else not have R? Okay, well, to
Most
turn
of
on
them.
R, okay, if you don't have R, you're gonna have to, I did this for everyone last class, so just please pay attention. So to turn on R, you're gonna hit second function, catalog, down here, second function catalog. Then everybody hit this X inverse button right here, where my mouse is. And then we're gonna scroll down. Rebecca, I'm sorry, I have no idea how to do this on a TI Inspire. You're gonna have to use YouTube, or as I said last class, let me just finish this, then I'll address that for you. Scroll down here till you see diagnostic on, and then just turn it on.
Hit enter.
Yep, if yours was already on, you didn't need to redo it. So you go over to calc, and it's number 4.
How do you get to calc? You hit the stat point?
You hit stat, and then you scroll over to calc. No problem, no problem. Rebecca, to answer your question, if you look under in the classroom, under the textbook and TI calculator link, I posted a link for an emulator. And if you have a Windows computer or a Mac, you can download the emulator and you get a 90-day free trial.
Oh, that's awesome. All right, thank you.
Yep. Did you, yep, no problem. To go back here, are you at least seeing R, Taylor? Okay, so if you don't have that number, you probably inputted one of the numbers incorrectly. That's all. Everybody else is getting the same number I'm getting? 0.9471. Okay, yeah, so you just,
I'll wait for the break.
okay. 0.9471. Okay, so that's my R. Okay, so look, this is close to +1. Okay, so remember, even just looking at the scatter plot, you know, we said it looks like a positive linear relationship. So this is close to +1. So this means there's definitely evidence for a strong linear relationship, strong positive linear relationship. Okay, but when I started this example, I didn't tell you what the variables X and Y were. I just said, you know, this is X and this is Y. So let me actually give you some context behind these numbers. So these numbers aren't made up, okay? What variable 1 is, it represents per capita cheese consumption. And this is in pounds per year in the United States. Okay, so what this means is, look, per capita means an average of everybody, the average for citizens in the United States. So a or people living in the United States. So what this is saying is, look, in 2000, people on average consume 29.8 pounds of cheese per year. And look what's happening over time. Do you guys notice that variable one is going up as time goes on? Does everyone see that?
Yeah.
Yeah, it looks like it, right? Variable number 2 here is the yearly deaths by being tangled in bed sheets. So it always does elicit a laugh, right? But it's actually like, generally it's infants who die by getting tangled in bed sheets. So it's actually a very sad statistic. But so look, over time, if you look what happens in the year 2000, it was 327. And then over time, it's gone up. Okay. So look, what we're saying here about the value of R is that these variables are highly correlated. Okay, that there's a relationship going on here. But do you think in reality, in the real world, do you think per capita cheese consumption has anything to do with the number of deaths by being tangled in bed sheets? So do you think they're actually related?
No.
No, they're not. Maybe you've heard of this saying before. All right, correlation does not imply causation. Has anyone ever heard of that saying before, just out of curiosity? Just because two variables are correlated together, like over time,
Yes.
okay, both these variables were going up, just because they're correlated does not actually mean there's actually any real relationship there. This is what's also referred to as spurious correlation. And it's what's called, there's this thing called a lurking variable, and I'll define that in the next slide or two. There's some other variable out there, and I don't even know what it is for this example, that's causing both of these variables to go up over time. And this is very common when you have two variables that are indexed to time. Like I can find any two variables that are going up as time goes on. Causation, Alexandra. I can find any two variables going up over time and get a high value of R like we did here, but they're not really related. So just because somebody says, or if you see a report that says these two variables are highly correlated, you got to dig a little deeper. You got to make sure that that's actually the case of what's going on. And look, I have a graph here that you can see that just over time, these two variables are going up. So I don't know, just always look out for that. Okay. There's actually some really interesting ones too. Like, I saw one that's really funny. That's how conspiracy theories start. Yeah, sure. Absolutely. I saw one that had to do with like Nicolas Cage box office revenue and like some other ridiculous variable that were highly correlated. And obviously they're not causation. Like there's just a bunch of really funny examples out there. Okay. So another way, as I was saying, that these two variables can be related, even though there's not a causal relationship, is what's this called, that lurking variable. So I don't know what the lurking variable is here. Okay. So a lurking variable is related to both the explanatory and response variable, and it's the variable that's causing them both to go up or down together. And like, let me give you an example of a lurking variable here. Okay. So ice cream sales and crime rates, especially over time, are very highly correlated. Okay. So what that means generally is that like during the winter, crime rates go down and ice cream sales go down. And that yet during the summer, ice cream sales go up and crime rates go up. Okay. Is ice cream sales driving crime rates? Like, do you think they're really related? Like,
No.
no, they're not. So what's going on here? The lurking variable that's affecting both of them is temperature, right? Like as temperature rises, ice cream sales go up and people are out more, so crimes are more likely to be committed. That's just what's going on there. Okay, but if you were to look at like, the value of R for these two variables, it'd be really high, but they're really not. There's no real relationship there. Okay. So the question then becomes next is like, all right, Matt, in all these examples you do, sorry, I'm going back really quickly. Like R is so close to -1. Like what if R was 0.7, 0.6, 0.5? Like what's the cutoff point for saying there is a relationship? And to do this, there's actually a quick test for linear relation, okay? And it's a 3-step procedure. So the way you're gonna do it is whatever your correlation coefficient is, you're gonna take the absolute value of it. So an absolute value just turns a value positive. So the absolute value of R for us here is just 0.9471. Then the next thing you're going to do is you're going to find what's called a critical value. And critical values are going to come up a lot in our class. And what critical values are, and a way to think about them, is they're like cutoff values. Did you notice how like last class when we were doing outliers, I said, oh, we have this cutoff value. And if you're above this cutoff value, you are an outlier. Do you guys remember that from last class?
Yes.
Yeah, it's like the same thing here. So I have the link to the table here, and I'm going to show you how to read it in a second. I also have it on the next slide here. But then what happens is that the absolute value of your correlation coefficient is greater than the critical value. All we say is, hey, look, there's a linear relationship that exists between the two variables. Okay. So otherwise, no linear relationship exists. So this is those critical values. This is the one from OpenStax. I don't like it. This is the one that I like here that I put here. I think it's just a little bit easier to read. And so I'm going to show you how to read this going back to our first example. Okay, so if you remember our first example, this was the output we got from our first example. It was the student grade scores. Forgive me as I go back real quick to this. So we saw here that there were 1, 2, 3, 4, 5, 6, 7, 8. There were 8 students that I had. And we said, look, the value of R for this, it was really, really highly correlated. And so when we ran our correlation coefficient in our calculator, this is what we got. So if you look at that table I gave you, this is the table for critical values. N is the sample size, remember. So look, I had a sample size of 8. And these values here on the table, going back here, see how it says critical values and then critical values? These are the critical value cutoffs right here. And so this is all it's saying. Look, if you have a sample size of 8, long as your value of R is greater than this number right here. So think of this as our cutoff value. Okay, as long as you're greater than this number, all right, we can say for sure that there's a linear relationship. And look, yes, that's absolutely what's going on here. The value of R that we're getting, okay, it's greater than our cutoff value. Okay, so that's why I've been saying things like there's strong evidence of a positive linear relationship. This is how we definitively say that there's this strong evidence of this positive linear relationship. Okay, so we're going to get some more practice with this. But I know I went through this pretty quickly, but at least is the concept of R, this linear correlation coefficient, makes sense? Is it, when using our calculator, it's not too bad to get?
Professor, how did you choose 8?
So if you look back That's our sample size. And so we had,
8 students. Okay.
Yeah.
Thank you.
no problem. And I'm going to do another example of this as we get further on. But for now, what's really important is everybody kind of feel a little bit more comfortable with their calculator, because we're going to use it a bunch in the next lecture. Okay. All right, if you haven't already done so, under course content, under week 3, I'm going to start this lecture number 2 now. Just answering the private message I got, we're going to get to practice more with the calculator. And so the best way to actually study for this, if you're having trouble with your calculator, is you take my notes and you see the, the answers that I've done in class. So what I would do is I would like cover up the problems, and I would practice with the calculator and work on the calculator till you can replicate it over and over and over again. Okay. Like these notes for the private message I'm getting, these notes, like these, I have all these problems worked in the notes. So I would like start with this one and calculate R. Okay, good. All right. I want to start this lecture now. And we're going to get to practice a ton with our calculator. So everybody have those handy. All right, we are now on the final topic before our first exam. Okay, so we've talked about correlation. Okay, and just to recall what correlation did, correlation measured the strength of the relationship, strength of linear relationship. And now what we want to do is with regression here, regression is about modeling the relationship. Okay, and what I mean by modeling it is we want to fit, I'm going to put that in quotations, fit the relationship with a mathematical equation. All right, we're going to fit it with a mathematical equation. And if you think about this, what we've been saying here is that this is all, there's a linear relationship that exists between the two variables. So does anybody have any idea what mathematical equation we're going to use? It's okay if you don't. Does anybody remember the equation for a line? Does anyone know what the equation for a line is?
Y equals mx plus b.
And that's exactly it, right? If there's a linear relationship is like on a line. So we want to fit this with a mathematical equation that y is equal to mx plus b still. Okay, so again, we're going to go back to this. Okay, so we're going to use our calculator for this. So what I want us to do, everybody grab their trusty calculator, okay? And this was the first example we did last class on this, but we're going to re-input it into our calculator. All right. So
My calculator has not been trusty.
say that again, Bob.
My calculator has not been trusty.
Oh, that's a shame.
It's all right.
Do I always say that in this class, the trusty calculator?
Yes, you do.
I do. My calculator's never let me down. Like when I need a ride to the airport or something, it's always there. It's just really good.
Very good.
That was a joke. Thank you for the one laugh there. Okay. But Bob, it'll get better. I wish,
Yeah, I'm not worried about it.
Yeah. I mean, when I first started teaching, when I was in college, and just a quick sidebar, this is for everybody. When I was in college, we didn't use the TI-84s or TI-83, so I had to like learn it as an instructor because I just never used it, or in high school we never used it. So like you just spend a weekend with it, and fooling around, working numbers, and it gets easier. Okay, anyways, to go back to this problem, we said that hours of study, this was our X variable, our explanatory. And exams grade Y, this was our response variable. So with your calculator, let's input this data again. Let's go stat. Under number 1, you have to edit the list. So what we have to do is we have to clear all this data out. Okay, so we're going to go to the top, clear, top, clear. And look, you have to put this in very carefully. It goes 1, 2, 3, 4, 6. There is no number 5 here. So 1, 2, 3, 4, 6, 7, 8, and 9. So L1 always gets the X variable. You're going to scroll over to L2 and you're going to input these in that order. So 50, 54, 60, 65, 78, 82, 85, and 88. And everything should be matched up perfectly. Okay. How many people are with me at least plugging it in the calculator so far? 1, 2, a couple people. All right.
Yeah.
Okay. So here's what we're going to do now. All right. When we looked at the scatter plot, this is what we saw. Okay. So even going back to your calculator, you can just hit zoom and then number 9 again, and you should see this scatter plot. Okay. And look, this is what we're seeing. We're seeing this linear relationship again. Okay. Okay, so again, we did just to rehash this, so we know that there is a strong positive linear relationship. This is just a replica of that other slide. Okay, so again, since we know there is a linear relationship between the variables, we want to describe or model the relationship with this mathematical equation. Okay, so what we're going to use here is we're going to use the equation of a line. All right, so this is that y is equal to mx plus b. First off, does anybody remember what m stood for in the equation of a line?
Is it the slope?
It's the slope of the line. Okay, so if you remember from your algebra classes, what slope represents is the rate of change. Okay, but yes, it's the slope. Does anybody remember what the b stood for?
That's your y-intercept.
Yep, the y-intercept. So now look here, the x and the y here, x, it's the explanatory variable. Okay, in this case, the explanatory variable was hours of study. And y in this case here, those are your exam score, or excuse me, is the response variable. And in this example, it is the exam scores. All right, so that's what we want to do, okay? I want to find the equation of the line that goes through the data like this, okay? So now here's the thing. Do you notice how like the data points are not a perfect straight line? Okay, there's no way to throw a straight line that goes through all the data points. But would you guys agree in the chat that line there does a good job of modeling the relationship? What do you think?
Yes, I think so.
Yeah, yeah, I think it does. I think it does a really good job. So this is what we want to do. We want to find the equation of that line. That's the whole point of this. Okay, that's what we want to do. The reason we do this is like it allows us to make predictions. Yes, Melissa, I'm going to talk about the best fit line in a second. Yeah, that's where I'm going towards this. So I want to find the equation of this line right here. Okay, so why do we need to do this? All right, so we model the relationship so we can estimate unknown values. Like for example, if you look here, nobody studied for 5 hours, right? So like if suppose you were like, oh, okay, well, I only have 5 hours to study for the exam, you know, what grade would you expect to get, right? It would be some grade between a 65 and a 78, but like what exactly, you know? So that's what this line helps us do. Or for example, if you were to study for 10 hours, you know, someone studied for 9, they got an 88, but somebody who studied for 10, you know, what would their score be? And the reason we do that, or how the line helps us, remember, this is the X variable, here's the Y variable. Here's X is equal to 5. If we know an equation of the line that tells us that, we can use this line right here to estimate the exam score. Or somebody that gets a 10. We can use this line to estimate their exam score with a 10. That's the whole point of this modeling the relationship here. Okay, that's what this line does for us. Okay, why we need to find it. Okay, so as Melissa says in the chat here, what we're actually looking for is what's called the best fit line. So there's actually an infinite number of equations of lines that you could pick from, okay? But there's only one out of the infinite lines that you could pick that actually best fits the data. All right, so what I mean by like, so this is our data. Does that line I drew fit the data well, do you think?
Not very, but yes.
Well, I mean, does it even go through it? Like, yeah, I don't think it fits it. How about that line? Does that line do a good job going through it?
No.
No. Does that one?
No.
No. Does that one? No. Like we're looking for this one line. Like that's just 5 lines, right? Or 1, 2, 3. Oh my God, I can't count. 1, 2, 3, 4. 4 lines, you know, out of an infinite lines that were horrible. But we want to find this one best fit line. Okay. So we can use this best fit line or least squares regression line. Okay, how we find it. This best fit line is called the following, and this is how it looks at here. This best fit line is found using what's called least squares regression. Okay, and this least squares regression will also be referred to as LSR. So here's the thing, you're going to hear me over the course of the remaining hour of class and Tuesday's class next week, refer to things as like find the best fit line or find the least squares regression line. It all means the same thing. Okay.
Quick question.
Sure.
When you mean the least square regression, when like the line that best fits, are you talking about like the line that has like the least squares that run through them, or like that's outside of them?
I'm gonna totally explain what least squares regression is. Like you're kind of hitting towards something, but I will explain. Hopefully, it makes sense what I mean by least squares regression. Okay, I'll get there.
Okay,
I
cool.
promise you. Yeah.
All right.
Okay, so exactly, what the heck is this least squares regression? So least squares regression is the line that minimizes the sum of the squared errors, okay? These errors are what are referred to as residuals, okay? So if you would just want a layman's term of what least squares does, okay? If you only want to remember one thing about it, just remember that it minimizes the errors. And I'm going to explain to you in a second what the errors are, okay? The technical term for an error in least squares regression is a residual. So this line minimizes the sum of the squared vertical differences, vertical distance difference between the observed values of y and what we call the predicted line, this y hat. All right, and I will explain this y hat in a second, okay? And we represent this minimum as the minimum of the sum of the residual squared. Okay. A lot of times, does it ever feel like sometimes when you have a professor that puts these definitions up there, you're kind of like, what are you even talking about? You guys ever feel that way? Yep.
All the time.
And I promise you, and the reason I preface this is a lot of times in this class, I'm going to put up a formula or a definition like this. And I wish I could see everybody in class, because everyone in class would just kind of be like, where are you, from Mars or something? What does this even mean? This y hat, these residuals. After you see a couple of examples, I promise it all makes sense. Like it's just, you just got to let me get there. Okay. I hope that makes you feel a little bit better. All right. So to go back, what is this y hat referred to? Okay. Do you see this line? This is the best fit line. Okay. We denote this line as y hat or y estimated, okay? So we've got to find the equation of this line, okay? Okay, so whenever you see the y hat, okay, it means it's the best fit line for the y variable, okay? All right, so what are these errors that you're talking about, Matt? Okay, these errors or residuals. Their equation is just equal to the y observed value minus the y predicted value, okay? So here's our data, okay? These little blue boxes are the actual data points, okay? And the red line through it is what we're saying is the y hat line. All right, look, here is the first data value, okay? Right here, this is x is equal to 1. This is what our line is saying we should get. Does our line actually touch the data value? Or is it a little below it?
It's below.
Okay, so here's what happened. The line is saying, the model relationship is saying you should score this value, but in reality, they scored this value. So did my line get it right, or was it off a little bit?
Slightly off.
Yeah, okay, so that's what I mean by an error. The model made a little bit of an error, okay? So it took the y observed value, okay? That's what we call y observed, it's the actual value. And you subtract away what we call the y predicted, and that is what the model, the line says you should get. And so what it does here, what I mean by it minimizes the sum of the squared errors. You make a little error here. Even you made a little error here, small error here, small error here, small error here, small error here. This one looks pretty close, but still a small error. And this one is a small error. What this does is it takes all the errors. Sometimes errors will be negative, sometimes errors will be positive, okay? Like if the observed value is below the line, it'll be a negative error. So what it does is it takes all the errors you would get, it squares them, and then sums them up. And this is the line. This is the line that produces the smallest amount of total errors, okay? If that helps thinking about it. So the smallest amount, put that in quotation, of total errors. Like if you were to do this line, imagine this line. Like look at how big the errors would be, right? Do you see the distance between the points in the line? Do you notice how like those errors are much, much bigger than these little small errors here? Does that make sense? So like this line cannot be the best fit line because this line down here does a better job. It produces a smaller amount of errors. And then there is no line better than this exact one right here.
So the line with the smallest errors would be the line that best fits.
That best fits the line. That's it. It just minimizes the errors. That's it. That's all the best fit line does. It's the one that gets
Makes
closest to all the points. That's the way you can think about it. I got one makes sense in the chat. Does that make a little bit more sense? I got another yes.
Professor, I was distracted here. Somebody just came in to fix something in my house. But I didn't understand the lines, just the smallest amount. I'm lost. Sorry, I'm sorry.
Yeah, I mean, it's pretty terrible, right? To be like, yeah, I wasn't paying attention.
I'm sorry, definitely. I'm so sorry. I'm lost. I'm very, very much lost.
I'm sorry. That made my day, right? But I appreciate the honesty. So all this is saying is like, look, this line is the closest to all the data points, and it minimizes the distance between the data points and the actual line. It's like it just minimizes the errors. Okay, minimizes the errors.
Yes.
All right, here's another visual of it so you can understand the residual here, okay? And then I just want to get through one more slide and then we'll take our break, okay? Suppose you have this, you can't really see them well on here, but these are the actual data points on the graph, okay? And there's actually one over here too. But look, imagine for this set of data here, okay, this line is the best fit line, okay? If you look right here, right, this right here is what the line is saying you should get, and this is the actual data value. So the line is making a little bit of an error, okay? So these are just made up numbers, but imagine that the real number here is 5.2, and the line is saying you should get 4.75, okay? The difference between 5.2 and 4.75, this value right here is the residual. And this line just found the residual for every single point and just minimized the sum of the squares of them. That's all the best fit line does, okay? And here's what we're gonna do. We wanna spend the hour that we have next, how do we find this best fit line? Okay, so there's 3 ways to do this, okay? You can do it by hand, all right? If it's okay with all of you, I'm just gonna show you the equation, and then I figure for less confusion, because we'll actually won't do it on the homework, on the exam, we'll actually skip that. This will be the one time in this class where I say, let's do it by hand, and then I show you the calculator. Are you guys okay if we just skip doing it by hand?
Yes.
Okay. Another reason I want to skip it just this one time is no one actually in the real world does this by hand, right? Like they all have a calculator or something, do it by hand. So what I'm going to focus on is using your calculator for this. And then if we have time next class, I'll show you how to use Microsoft Excel for it if people are interested.
I am.
Yeah.
Something's got to be better than this calculator.
That's fair. That's fair. That's fair. All right. So I do want to focus on the calculator because we all have it, and then I'll show you Excel next class. Okay. Let's take a little bit of a break. Um, let's come back at 2:05, okay? We'll take a 10-minute break. Does that sound okay with everybody?
That's okay with me.
Yep.
Yeah.
All right, we'll be back in 10 minutes. Can I see slide 11? Sure. Here you go. Here's slide 11. So we'll take a 10-minute break. We'll be back at 2:05. I might do a little work on my computer that you guys will see. I'm so sorry. I forgot to load up the YouTube video. So I might try to do that during the break. Okay, everybody?
Beautiful. Oh.
All right. Can everybody hear me okay? Just checking my mic again now that we're coming back.
I can.
Yes.
All right.
All right.
So what I want to do now is I want to go back. Everybody make sure they have their graphing calculator, okay? And what
Not
you
trusty?
yes, the trusty graphing calculator. Hey, we all have idiosyncrasies, right? Like this is mine, the trusty graphing calculator.
You're the boss.
And what you want to make sure is that you have the data, okay, from this example plugged in, okay? Because what we're going to do is we're going to work this entire example, finding the regression line, plotting it, the whole deal, the whole kit and caboodle for it, okay? And you want to make sure that you can see the box plot here, okay? Does anybody need to see me put up the data again to plug it into their calculator?
Yes, please.
Okay. Okay, so it's this data right here, okay? So if you haven't done so, you're gonna put hours of study under L1. Julia, what it means is you probably don't have your stat plot on, okay? So if you hit stat plot on your calculator,
It
just
says
make,
on
it says on,
with like the picture of the scatter
and it has the picture of what?
of the scatter plot.
And what is it? So, but you get the value of R. What is it? What type of error does it say?
It says just error syntax, but I got the same R value as you.
That's really weird. You sure it says, it looks like it says plot one, it says L1, L2.
Yeah, it says plot on. Yeah, it looks just like that.
You might have to restart your calculator and redo all the settings. But do it after class. Just pay attention to what I'm doing here.
Okay.
And then, all right. Bob, are you okay if I go on or do you still need the data?
Forge ahead, young man. Go ahead.
All right.
Thank you.
Okay. So this is the actual equation for the least squares regression line. It's actually a pretty straightforward problem to do by hand, but it's actually a little bit easier on your graphing calculator. Okay. So this is how I will write the least squares regression line. Okay, and you'll see why I change this a little bit. It's y hat is equal to, and I'm going to change it. If you notice here, it says B1 and B0. I'm going to write it as AX plus B. Okay, so just in the notes here, I am just changing the notation. I'm not going to use the MX plus B. You'll see why in a second. Okay. And what this y hat stands for, okay, it is the predicted y value. Okay. And the y value is our response variable. The x here, the x is always our explanatory variable. And for this equation here, a is going to be equal to the slope and b is going to be equal to the intercept. Okay. So if you wanted to follow it by hand, okay, or to do this by hand, you could just follow these equations here. So the slope A is equal to, what does R stand for again? We've been talking about it for the first hour of class. Our calculator gives it. It's the correlation coefficient. So you would take R and you would multiply it by S sub y stands for the standard deviations of the y variable divided by the standard deviations of the x variable. If you were to plug that into your calculator, it would give you the slope of the regression line. You could then find the intercept next. You would take X bar, we know is the X bar stands for the sample mean of the X variables. Does anybody know what the Y bar stands for then, do they think? If X with a bar over it is the mean of the X variables, what do you think Y with a bar over it is?
The population.
No, the mean of the what
Sample
variable?
mean? Sample mean?
The mean of the Y variables.
Oh,
So you would take the mean of the Y variables minus the slope times the mean of the X variables. And that's how you would get your intercept. So look, we're going to have our calculator do this for us. Okay. And I just want you to know, like when I did the correlation, I said, here's the formula for the correlation coefficient R, but we're never going to do it. We're going to have our calculator do it. It's the same thing here. Okay. So this is the equation that I will always write. Okay, are we ready to do an example? You ready to finally jump into this and get the equation? I hope so.
Yes, I love adventures.
Okay. All right. So let's find the least squares regression line from our example. Instead of using the formula, let's just do using our calculator. And then after we find it, what I'm going to do, you'll see, is I have a bunch of questions for us. Okay. All right. And then we'll talk about how you answer those questions. All right. So this is the equation we're looking for. All right. Y hat is equal to AX plus B. Okay. A is the slope. B is the intercept. So everybody grab your trusty calculator here. Notice how I did say trusty finally. Okay. And you're going to hit your stat button. You're going to scroll over to calc. And what option did I say we use to find the value of R, the linear correlation coefficient?
4.
Yeah. Do you notice how it says lin reg AX plus B there? Does everybody see that on their calculator for option number 4?
That's your equation.
Yeah. So yeah, here's the thing. What lin reg stands for is linear regression. Okay. Linear regression is also synonymous with the least squares regression. So if we scroll down here, all right, and hit enter and scroll down to calculate, or if you have the TI-83, just hit enter. You should all see this again. Okay. All right. How many people see this exactly on their screen as mine? Kayla does. Does anybody else? Melissa? Yep. Julia? Right. So here's the thing. We've talked about R. R is the linear correlation coefficient. Great. R squared, we're not going to worry about in this class, but it's what's called the coefficient of determination. And look, this is amazing. Right at the top, it says, okay, Y is equal to AX plus B. And do you notice how it tells you what A is right here and what B is right here? Does everybody see that? Yeah. Okay. So it's saying, I'm going to round this to 2 decimal points. It's saying A is equal to 5.03 and the intercept is equal to 45.08. So what your calculator did, just to save us time, is it did these calculations for us right here. Okay. So now what we're able to say is our least squares regression line. Okay.
Oh my God, it came up. Oh, I'm sorry. I'm sorry.
That's okay.
I hit enter twice and it popped up. I got your numbers.
That's good. All right, so the least square regression line for our example is the following. All you have to do when I ask for the least squares regression line is to put these values in. Y hat is equal to 5.03 times X plus B. So this is 45.08. All right, so now just so we're clear what all these things are. X is our explanatory variable. What did we say X is from our example? Is it hours of study or exam grade?
Hours.
Yeah.
Hours of study, yeah. And what y hat is, okay? Y hat predicts something, okay? And what was our y variable then here? If it's not hours of study, it has to be,
Exam score.
yeah.
Cool.
Yeah, so y hat, what y hat is, it's the predicted exam score. And this is what this line does. They say, okay, look, I've modeled the relationship. So if you tell me X, if I give you X here, okay, I'm going to be able to plug it into my equation and I'm going to predict somebody's exam score. That's how we're going to use this equation. All right. That's the whole thing here. That's everything that's going on. All right. Does everybody have all this stuff I have on the screen written down?
Yes.
Everybody okay if I go on? We can actually do some examples now or work.
1 second.
Okay, no problem. I can wait a second.
All right, you're good. I'm all set.
Okay. Dun, 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 dun. So I got some questions here. Let's now plot the line in our calculator. And my question is, does the line fit the data well? All right, so I want to show you in your calculator now how you can put the line on top of it. All right, so everybody grab your calculator again. And do you see this y equals button right here? Does everybody see that on your calculator?
Stat plot?
Yeah, right below stat plot, but don't hit second function stat plot. Just everybody hit y equals on their calculator and you should see something that looks like this. Do people see that? I got a couple of yes. All right.
I got it.
So what I want to do is I want to take this equation, this 5.03x plus 45.08 and plug it in. So notice how it says y1 is equal to. So it already has the y variable in there. So we're going to put 5.03, that's our slope. And then look where my mouse is. Everybody sees my mouse flying around on the screen? This button right here, okay?
You hit enter after you put 5.03 in?
Nope. Just at 5.03. And then, does everybody see where my mouse is over this thing with X comma T right here?
Yes.
Click that button next. And you'll notice it puts an X there for you. That's the variable button. Plus 45.08. And you should see this. Okay. You can hit enter now. Okay. 5.03x plus 45.08. And now everybody, if you have this in here, let me hit graph, hit this graph button on your calculator right here. And you'll notice what happened is it drew the line right on top of your data. Does anybody see that on their calculator? Anybody able to get that with me?
Professor, when you hit plus 45.08, what did you do next?
So when you're here, so I just went 5. Let me clear all this out so you can see it again. I went 5.03, this button, plus 45.08. You can even just hit graph at this point and it'll still put it up there for you. Just as long as you see this in your y equals 5. So I got a couple no's. When you got no's, did you not see the line at all? Was it?
I got it.
I know, but I got a couple no's in the chat.
Okay.
There's nothing in my screen. It's just blank.
Were you able to see the when you hit zoom number 9, when you hit zoom 9, do you have the data plugged in for this?
Oh, okay. Now I see it. I see it.
Yep. If you hit zoom 9, hopefully you see it then. Okay. Okay, great. All right, so people got it now. Great.
We would always have to do Zoom 9, like whenever we wouldn't see it.
Whenever you change your data in your calculator, yes, you should hit Zoom 9. Okay.
That's the man. I got a line, but it's on like the top left quadrant. I don't know why.
It's not on top of your data.
No, it's just got, I don't have what you have. I got a box, I got a square and a line going on the top left quadrant.
So generally what that means, Bob, is you inputted something wrong. Like,
Later on again. Okay, thank you.
yeah. I'm sorry. It kind of stinks doing this remotely because I can't, I think I said this last class, like I can't grab anybody's calculator and be like, hey, this is what you did wrong. You know, like it's brutal.
That's not the word.
Yeah, well, we're recording, so we won't say what the word it really is. Okay. All right, so look at this. My question for you is this. Does my blue line fit the data? If it's a box, maybe the wrong graph type is selected. Yeah, that's true. Melissa said that. Like, Bob, if you look under stat plot, does it have the scatter plot here?
How do I get to the stat plot again? I hit stat?
You hit second function stat plot.
Oh, yeah, I got that doohickey.
So you
How do I get over there?
under number one, edit. Under number one here, I mean, you just hit enter. And you scroll down to type.
Mhm.
And you just make sure you hit enter on that.
Okay, got that.
And then just hit zoom. And then number 9. But for now, Bob, just follow along with me. And then, I should have 10 minutes after class to be able to help you a little.
Thank you.
Yeah, you're welcome.
And
So the
thank you,
question,
Melissa.
I'm sorry?
And I said, thank you, Melissa.
Yes. Thank you, Melissa. The question was, does the line fit the data well? Look at this. Does this line look like it goes through here like near perfect? So the line, the dots are not a perfect straight line, so it can't touch them all, but yeah, like it fits it like well, it fits it near perfect. So it turns out there is no better line. This is it. This is the best fit line right here. So yes. The line fits the data well. So the next thing it says is use your LSR line, your least squares regression line, to estimate the exam score for somebody who studies for 5 hours. Okay. So this was our equation. Our predicted exam score is equal to 5.03 times X plus 45.08. Okay. If you look back here at our data, there is nobody who studied for 5 hours, right? There is no 5 here. Okay, it's missing. So I want to predict someone's exam score here. Can anybody tell me what I can do, how I can use this equation to predict their exam score?
Plug in for X.
Yeah, that's exactly it. Look, I'm telling you that they studied for 5 hours. So you're given that X is equal to 5. So exactly, all you're gonna have to do is plug this value in. So Y hat, our predicted exam score, is gonna be 5.03 times 5 plus 45.08. So I'm just going to grab the trusty calculator. And I'm going to go 5.03 times 5 plus 45.08. Thank you. Look, Julia got it too. We're predicting that if you only study for 5 hours for this first exam, you're going to get a 70.23. All right, so let me just write this out. So this is just so you can understand exactly what's going on. We predict an exam score of 70.23 for someone who studies for 5 hours. So on the exam, it'll say how many decimal places to round to. Also, just so you guys know, on an exam, I build in a tolerance. So like, for example, if the correct answer, this is a little bit of a tangent, but if the correct answer is something like 7.15 and you put in 7.2, I'll accept it. Because I'll build in a tolerance to accept a range of values, because sometimes people forget to round correctly. Does that answer your question, Bertha?
Yeah, it does. Thank you.
Yep, no problem. Okay, next it says use your least squares regression line to estimate the exam score for somebody who studies for 10 hours. Okay. So what do you do here?
Wouldn't that be for plugging again?
Yeah, same question. Look, if looking back here, look, I don't have an X value of 10. Okay, I don't. So what I want to do is I want to predict somebody who's going to spend 10 hours, you know, the night before or the week before studying for the exam. Okay. So again, you're given X is equal to 10. So you just have to plug this in. So y hat, the predicted exam score, is equal to 5.03 times 10 plus 45.08. All right, yeah, you guys are. Now I'm going too slow for you guys here. Yep, you got that 95.38. All right, so again, just what's going on here. We predict, I don't know why I put and an exam score of 95.38 for someone who studies for 10 hours. Okay. All right, here's the last question for this problem here, okay? Let's find the residual, all right, when X is equal to 4, okay? So what was the residual? What was another word for the residual? Started with an E.
Error.
Yeah, I want to find the error, right? So let me just go back and find the formula for this, okay? Right, so the residual or error is the Y observed minus the Y predicted. Okay. So now here's the thing. The Y observed is the actual Y value. And what did we call Y predicted? What did it had the Y with the what on top of it?
Hat.
Yep. And the Y predicted is Y hat. Okay. So let me go back here. I'm going to go back one slide real quick. Okay. It said find the residual when X is equal to 4. Here is X is equal to 4. Okay. What is the actual Y value for somebody who studies for 4 hours?
65.
Yep, they're going to get a 65 on the exam, okay? Or they got a 65. That's what the actual data says, okay? All right, how could I find Y predicted? I have no idea. Awkward silence. Do I have an equation that gives me the predicted value of y?
Yes.
Totally. Yep. Yep. That's it. Right. Y predicted, y hat is this equation right here. So to find the what the predicted value is, I'm going to take x and plug it in. So to find y predicted, plug in x is equal to 4 into equation. So my predicted, that's what y hat is. Y predicted is equal to 5.03 times 4 plus 45.08. So we would predict that the person would get a 62.5. That's what we're saying here. Okay. 65.2. Sorry, I said that backward. So the model was like really close, but did it get exactly right? Like the person actually got a 65 and the model said they should have got a 65.2. So was the model off a little? Yeah. And that's the error. So the actual value was 65. The model said they should have gotten 65.2. So the residual, when you do 65 minus 65.02, is minus 0.02. So it was really close, really, really close. All right. So where did I get the 65 from? So it's the y observed. So the y observed is also the y actual. So I'm telling you x is equal to 4. So remember, hours of study was our x variable and exam was our y. So when x is equal to 4, that's okay, great. Okay, not too bad when you, at least for this stuff, was it easy with the calculator to find the equation of the line? I mean, your calculator just gives it to you, right? Yep. And then you just have to, you have to plug things in for this, okay? So I want to end on talking about the interpretation of the slope and the intercept, okay? So we know in mathematics that a slope gives us the rate of change. Okay, so what we're saying here in our model, we're saying the rate of change is 5.0. I rounded to 2 decimal places here. All right, but the rate of change of what, right? Like, so this was our equation. Okay. And when we say this is the rate of change, what we're trying to find is the rate of change of exam scores, okay? Exam scores. So the slope here tells us how much y will change when x changes by 1. So what this is saying is y will change by 5.03 when x changes by 1. So my x variable is the hours of study. So if you study 1 additional hour, so every additional hour you study, the slope is telling me how much your exam score will increase by. Okay, so for every hour of study you put in, we would expect that and I'll explain why on average, you should go up by 5.03 points on your exam, okay? The reason we say on average is every single person's different, right? And like this is modeling data values on individuals. So like somebody's additional hour of study will benefit them more than somebody else. So that's why we just say this line just gives the average of everybody. That's what this line is giving us. So you should be studying quite a bit. Okay. So for every extra hour you put in, just know your exam score is going to go up roughly 5 points. Okay. Does that kind of make sense with the slope for the rate of change? For every additional hour you put in for X, Y should change this much, the slope. Y changes by the slope for every additional 1X. Thumbs up, thumbs down.
Up.
Up. Okay.
Makes sense.
Now the interpretation of the intercept is really tricky. Okay. So this is why I mean by it's tricky. The slope, you always can interpret the slope. The slope of the regression line is the most important thing, okay? Because it gives the rate of change of Y. This is where it gets tricky. Sometimes you can interpret the intercept and sometimes you cannot interpret the intercept. Okay, sometimes the intercept is just noise. So the Y-intercept here, we see with this regression line was 45.08. Okay, so if you're going to interpret the Y-intercept, you have to ask yourselves these two questions first, okay? Is 0 a reasonable value for the explanatory variable? Okay, so remember the explanatory variable is hours of study. Could you study for 0 hours for an exam? Can somebody not study at all? Is that reasonable?
No.
Well, I don't mean like, should you do that? I mean like, do you think somebody will not study for the exam?
Yeah.
Yeah, it's reasonable. You know, it's not unreasonable in the terms of this example that someone's going to be like, it's Sokol's class, I'm going to wing it. So yeah, it's totally reasonable. And then the next thing you have to do is you have to look back at the data set. And it's one thing for it to say it's reasonable. Another thing you have to have is you have to have observations near X is equal to 0. So if I look back at my data set, I have values of X close to 0, right? 1 and 2 are pretty close to 0. So you have to have values close to 0. So yes, we do. Okay. So again, a value of 0 is reasonable since it's reasonable for the model and we have values close to it. So that means you can interpret it. Okay. So what this means is when you interpret it just like Y-intercept. When X equals 0, we predict Y to be 45.08. So what that means in the terms of the context of the problem, if a student's going to study for 0 hours, we predict that they're going to get a 45 on the exam. Okay. So what this also means is so you should study for your exam. Okay. All right. So one thing about this least squares regression line that's important is if you use the least squares regression line to make predictions based on values of the explanatory variable that are much larger or much smaller than observed values, we say what you're doing, the researcher or the person working on it is working outside the scope of the model. So what you never want to do, you never want to use this least squares regression line to make predictions outside the scope of the model, because what you can't be sure is that a linear model still exists. Like, let me go back. Do you notice how I only have hours of study up to 9? X is only up to 9 there.
Yes.
You wouldn't want to use this least squares regression line for somebody who studies for 20 hours. Okay, you wouldn't want to do that, because what would end up happening in reality, if you look back at our scatter plot for this data, I bet that for the first few hours of study, it's a very linear relationship. And then what happens is the additional hours of study just stop being beneficial. Like it plateaus. So it stops being linear, because once you get outside the scope of the model, the relationship is going to change. So we're only going to use these regression equations, for values that are between observed values. So like to predict something between 1 and 9, or for values just outside of 1 or just outside of 9. So that's what you use this regression equations for. You don't use it to predict model values that are way, way, way out there. Okay. I'm going to actually end class 10 minutes early, if that's okay with everybody. Does anybody, because I don't want to start a problem. I'm not going to be able to finish any of these problems in 10 minutes.
That's fine.
Okay. While I got you here, let me say a few things. Tuesday, all we're going to do on Tuesday is just do 2 more examples of this. Okay. So have your calculator handy. As you can see in the slides here, I have one example here where I ask a bunch of questions, and then I'm going to do another example here. Just so you can see more of these problems. Okay. And that's what we'll do during our first hour of class or so. Okay. And then during the second hour of class on Tuesday, I'll do a review for your first exam. Like I'll just do problems that you might see on the exam. And then I will also answer any homework questions too. So like I would spend the weekend trying these homework questions. Okay. You can do all of problem number 6 now. There's only one problem on here that I haven't done, which is this last one here, but I bet you could figure it out. And I'm going to do a problem like that in class on Tuesday though, but you can do every other problem. All right. And look, at the end of the day, if you do this homework and you spend a lot of time on it, you're going to be really, really well situated for the exam. Okay. So while you guys got me, does anybody have any last minute questions?
I just have one.
Sure.
So when you say like find the least squares regression line, is that just what we did on the calculator?
That's it. Least squares regression line is the same thing.
So how do you answer it? Because I know that's a question on the homework.
Yep. What the answer to the least squares regression line? Let me get it. Is this right here?
It's the equation. Okay.
Yeah, it's the equation. It's
Got
this
it.
right here.
Okay. Thank you.
Kenneth, Tuesday's lecture. Let me just stop the recording.